this webinar, this is going to be a part of a new set that we're trying. Introduction to Signal Integrity for PCB Design. My name is George Garcia. I'm a product support specialist with Autodesk Eagle and have been working with Eagle for about the last 10 years. So it's a pleasure to have you all here on this webinar. And to start off, we really want to say that signal integrity is a very broad and vast topic. You know, there's no way that a 30-minute webinar could even hope to begin to scratch the surface of signal integrity and its nuances and everything that can be involved in a design where you have to take signal integrity into account. So to start off, we really want to kind of define when should you start worrying about signal integrity. So to make that definition, and before we continue, if anybody has any questions, feel free to post them. We'll be leaving them for the end. At the end, we'll answer any questions that pop up during the webinar. So feel free to post them either through Q&A or through the chat. At the end of the webinar, we'll be answering them. Okay, so don't worry. We'll make sure to go through all of your questions. So the key thing we kind of want to define is, when do we have to start worrying about signal integrity? The technical answer is that signal integrity is always at play. You know, the effects that we're going to consider in this series of webinar are always there. But at low enough frequencies, they're so small that they can be ignored. And this is why many of you maybe have never even had to worry about signal integrity, have never had to really consider some of the topics we're going to analyze, because your designs have been in a regime where the rise times and clock frequencies are high enough where this becomes an issue. So if you're thinking, I've made a ton of boards, I've never thought about any of this stuff, why is it important to me? Well, if you have never needed to think about it, it's because your designs so far haven't required it. But as technology continues to advance, clock frequencies continue to go up, rise times continue to go down, modern products, you know, high-speed USB, PCI buses, things like that, in those situations, it is critical to be aware of your signal integrity. It is critical to design for it, because if you don't, you can have products that don't work. And that's going to create delays in your schedule. That's going to create issues in your ability to go to market. So that's why this is important. You need to take these into account, and being aware of them now can help you make better design decisions later. So we're going to go ahead and get started. The first thing we want to determine is, when do I need to start to worry about signal integrity? So let me get out of this shot. We're going to go to Eagle. And this is a little presentation that I've used before, and we're going to use aspects of it in this webinar. Okay? Signal integrity becomes a very big deal generally when you're dealing with what's known as the high-speed regime. Now, the definition of a high-speed signal is a little bit gray. Okay? It's not a clear-cut definition, but it can give you an idea of when you need to start taking these effects into account. And one of the key things of dealing with the high-speed signal, and where signal integrity has a big role, is that when you're in this regime, when you're dealing with a high-speed signal, your wires are no longer transparent to the signal. In other words, they can't be ignored and treated as a perfect conductor. Rather, as you can see in this Eagle sheet, your wires in the high-frequency regime, because these types of circuits, okay, they have to be treated as a transmission line. And this is an approximation of a transmission line using what's known as a lumped parameter model, okay, where you're modeling the impedance of the transmission line with resistors, capacitors, and inductors. Okay, so when does life become hard for us? When can we no longer ignore the wires in our circuit and have to start treating every single interconnect as a transmission line? Well, what you want to do is you need to look at the frequencies in your design. Okay, this particular metric is coming from a high-speed layout guidelines from TI. I have the document number reference there in the slide. or in the sheet. Okay. And what they recommend is find the highest frequency in your design. Now, the highest frequency in your design is determined by the fastest rise time in your design. So you can have a 10 kilohertz signal, okay? And let's say, you look, oh, 10 kilohertz, I should be more than fine. 99.9% of the time you would be. If that 10 kilohertz signal, if the edge, as you can see here, has a very quick rise time, it's a very quick edge, something on the order of 1 nanosecond, then you need to treat it as a transmission line. You're in the high speed regime. So don't let just the clock frequency dictate whether you have a high speed signal or not. You have to make sure that you look at the rise time. That's generally the more subtle point where people don't realize that they are dealing with a high speed signal. Okay, if the rise time is very quick, and by quick we're talking on the order of a nanosecond, 1, 2 nanoseconds, you need to start kind of being careful. You need to start thinking about, is this signal a high-speed signal, something I need to be extra careful with? So we can see an example here. Okay, if you notice, we have a square wave, and the rise time of that edge is 100 nanoseconds. Now, based on what I just said, we know that this is probably not an issue, not a high-speed signal. Okay, but if we go ahead and take the reciprocal of the rise time, we're looking at about a 50 megahertz signal. We're going to look at the length of that signal, so the length of that waveform. So first thing we need to do is calculate how fast the signal is moving through the PCB. Okay, and the speed is basically calculated by the speed of light divided by the square root of the relative permittivity of the material. So that sounds like a whole bunch of jargon. Basically, the velocity of the signal through your board is the speed of light divided by 2. Okay, because for FR4 material, the relative permittivity is 4, square root of 4 is 2, speed of light divided by 2 gives you approximately 1.5 times 10 to the 8th meters per second. Okay, pretty straightforward in the math of it. If it seems like a lot, just realize that this is kind of a definition, a derivation of where we make this determination. As soon as we finish going through this math, I'll give you a rule of thumb that is easier to remember than going through this math. But this derivation is insightful, so we're going to go ahead and finish it. So the wavelength of this type of signal is basically the speed that it's moving through your board, it's propagating, divided by the frequency. So if we notice, we got the frequency is 50 megahertz. We got the speed of light, the speed of the signal traveling is 1.5 times 10 to the 8. The wavelength, if you do the math, works out to be 3 meters. Okay, 3 meters. So if your traces are considerably shorter than 3 meters, you can ignore the interconnect. You can treat it as you always have, as a completely transparent. So what is a lot less than 3 meters? Well, TI defines it as 1/10 the wavelength. So 1/10 of 3 meters, 30 centimeters, about 12 inches. So if your traces are less than a foot, you're golden. You don't have to deal with any of this. Okay? But if now you're dealing with traces that are much longer, which obviously in most cases that wouldn't be the case, 10 feet, 12 feet, you do have to take this into, you're basically dealing with signal integrity issues. Okay? So what is the good rule of thumb? What basically can simplify all of this, and just something that if you run into it, you can say, I need to be careful with this. Okay? The rule of thumb, as defined by Signal Integrity Simplified by Eric Bogatin, which is a very good book if this is something you're going to be dealing with a lot. If you're working in USB, IoT, anything with high-speed communications, definitely I encourage you to get that book. Very good practical application of signal integrity concepts. The rule of thumb he gives is basically if you have clock frequencies above 100 megahertz or rise time shorter than 1 nanosecond, then you're dealing with a high-speed signal. Okay? So clock frequency higher than 100 megahertz, rise times shorter than 1 nanosecond. You're dealing with a high-speed signal. Okay, and if you're dealing with a high-speed signal, you have to treat every interconnection as a transmission line. And that's where things become more delicate as you're working through this. So let's take a moment and kind of discuss the rules of thumb, okay? In signal integrity, every equation that is used, everything that you see here, is either a definition or an approximation, okay? It's either a definition or an approximation. Some are very good approximations, but they are approximations nonetheless, okay? What's the point of saying that? Okay, if you're working at a company and you're going to start making PCBs and you have high-speed signals, okay, you don't want to lose a $10,000 run of boards, okay? So the best way to confirm the operation of your design before you manufacture it in the signal integrity world is you have to do simulation. So simulation is a big part of signal integrity design and analysis. There's just no way around it. Basically, that's the most accurate way to verify your design. Approximations and rule of thumb can give you a good answer now, but if you need an excellent answer, if you need high accuracy, you have to go with the simulators. You can't really do these types of analyses by hand. It just becomes intractable. So luckily, there's a lot of tools that have become available. And maybe another webinar we'll go into talking about them. Initially, though, SPICE is a very good way to start, and you can cover a lot of ground with SPICE. So in future webinars, we'll be going over that. But this is a key concept you want to have in mind. Is, do I have high-speed signals in my design? Once you can make that determination, then you know if you have to go through the concepts that we're going to deal with now, or if the design is basically transparent and pretty much any route will work, okay? From the signal integrity point of view. Obviously, high power, there'll be other considerations, but from the signal integrity point of view, the first thing you need to do is determine, do I have high-speed signals? Am I in the high-speed regime? If I'm not, then I can relax a little. If I am, then I have to be very careful. And again, if you're working for a corporation and you have products that need to go to market, simulation is your best friend. You are going to have to go into simulation because in general, all of the equations, all the formulas we're going to run into are on some level an approximation. So keep that in mind. So what's the next concept that we want to kind of introduce for signal integrity and that we'll be talking about a lot in future webinars, okay? Next concept that we want to discuss is impedance, okay? Impedance is the key parameter in signal integrity. It basically gives you every important electrical property about an interconnect. So you need to become very familiar with the idea of impedance, okay? For most of us who've worked with electronics for any amount of time, it should be very familiar. It's basically the relationship between voltage and current. It's the ratio of voltage to current. In a resistor, it's a steady value. It's very simple. It's basically always whatever the resistor value is. But now when you're dealing with inductors and capacitors, you have a frequency-dependent impedance, okay? So impedance is more general than resistance. You can always talk about impedance. You can't always talk about resistance, okay? So that is the key term, and you're going to see it pop up a lot. And to further that discussion on impedance, let's look at this sheet, okay? So why is impedance important? Basically, impedance dictates how your signal is going to interact with an interconnect. Okay, and we have a very simple example here. Okay, we have a driver going into a transmission line with a characteristic impedance into a load. Okay, very simple. Now, in order for signal integrity to be preserved, the signal wants to see a constant impedance as it travels down the trace. Okay, if there's ever a discontinuity, if there's ever a difference in impedance, then your signal is going to distort. You're going to get what are called reflections. Okay, and that's what we're showing here. So as you can see, we have just a simple square wave coming in, V sig, into the transmission line. Okay, if the load matches, in other words, is the same impedance as the transmission line, then V out is going to be pretty much pristine, okay, or is ideally going to be pristine. And that's what you see here. However, if it's mismatched, you're going to get reflections, and those reflections are going to manifest as squiggles, you know, as higher harmonic components in the signal, as you can see here, or distortions. Now, if you've noticed, I've drawn a little dotted line through the middle, okay? And this is basically representing a detector threshold, okay? So imagine digital logic. Anything above that threshold is a high. Anything below that threshold is a low, okay? If you get signal distortion because you don't have the impedances matched, well, if you notice, these reflections are very close to that threshold. In other words, if the impedance mismatch is large enough, you can get your data corrupted, okay, and your product will not work. So it shows you what a fine line, how critical this can be here, okay? So if you're in the high-speed regime, one of the big fundamental rules is to maintain constant impedance. And how do we do that? Basically, you make sure that your trace width is consistent the whole way through. Okay? If you can avoid vias, you totally should, because a via will affect the impedance. It will be a discontinuity in impedance. There will be a difference there. You will get some reflection. Now, obviously, you can't always avoid vias. And in future webinars, we'll analyze, well, when can a via, you know, what can you do to make the via safer? To make the via as transparent as possible to the signal. And those are things that have to be really taken into account with high-speed boards, where now you have different materials, different things that you have to deal with. Okay, so that's what we would kind of keep in mind here that we're discussing. Maintain the thickness of your traces. In doing so, you maintain a constant impedance, and you can get cleaner signals. Now, obviously, depending on the type of driver, the driver may have an impedance that it wants to match to, but your transmission line will have a different impedance, and in those cases, you'll have to do things to equalize them. But having it constant is going to make your life easier. Okay? So what are things that can create impedance discontinuities? If you have to alter widths halfway through your trace, that can create reflections. Okay? Depending on lengths and things like that, they may be serious, they may be not. So again, in other webinars, we'll go into more detail about this, but that's something you want to keep in mind here with signal integrity. Impedance matching is vital to maintaining signal integrity. Any impedance mismatch will create distortion in your signal, and that can lead to your product not functioning properly. Okay? So let's show you a common example here. Okay? As we know, op-amps in general have very high input impedance. Now, I just chose a random op-amp. In case anyone here is very much a signal integrity expert, I know a 741 would never be used for such an application. I just had to put in an op-amp. Okay. So if you notice, if you just take the transmission line straight to the op-amp, okay, you have whatever the impedance of the transmission line is going into an extremely large impedance. Okay, there are going to be reflections. Now, obviously, if you have low-speed traces, low-speed signals, you don't have to sweat it. You know, that's okay, because we've all done this. You know, if somebody tells me they haven't, they're lying. You know, because we've all done this. We've all just taken connections straight from component A into the op-amp. Okay, we've all done it. We all do it, and most of the time it's okay. But in a high-speed situation, that's not going to work. Okay, and the reason is you're going to have that impedance mismatch, and you're going to get a ton of distortion on the signal. So by using, and this is one way to terminate. There are many ways to do termination. There are depending on the situation, but this is possibly the simplest one, okay, is to put in that load resistor there in parallel, because what's going to happen is, you know, a high impedance in parallel with a lower one, the effective impedance is going to be the lower one, basically, okay, and that will help minimize distortions. So keep that in mind, okay? These are just very fundamental things we're going through over here. In this webinar, in future webinars, we'll go into more details, okay, and we'll analyze specific concepts and things that we can do. But this webinar is intended to be just a general overview. Now, what's the next concept that we want to discuss? And this is the last one we're going to discuss for our webinar today, and that is ground, okay? We're all used to ground. We all talk about ground. You have to be very careful with the word ground in signal integrity, okay? And really, you always should be. But now, once you're dealing with high frequency signals, the understanding of ground needs to change a little bit, okay? And we need to kind of expand on it, become a little bit more nuanced and a little bit more specific with it, okay? So what we want to keep in mind here is that most of the time, when we talk about ground, it puts our mind into thinking that ground is basically just a huge current sink. You know, all of our signal ground currents, they just go into this one big place. Okay? And that is completely and utterly false. That is not true. Okay? If you were to, if you need very expensive equipment to illustrate, to see this physically, but when you start analyzing, okay, and we all know this fundamentally, but because of, you know, daily practice and working, sometimes we lose sight of this fact. Electricity current always flows in a loop. Okay, for every signal, you have the current going through the signal path and then coming back through a return path. Okay, every signal on your board does this. It goes out and the current flows back. Okay, for most of us, we just let it flow to ground. Okay, but if you have the proper equipment, what you're going to notice is that when the current goes back through the ground plane, it's not evenly distributed through the ground plane. It actually wants to follow the signal path as closely as possible. So what you're going to see is that currents in a ground plane do everything they can to flow right under the signal path that originally created them. Okay? And the reason for this is to minimize inductance, is to minimize impedance. Water flows through the path of least resistance. Current flows through the path of least impedance, always. Okay, and the path of least impedance occurs closest to the signal trace, right underneath it. Okay, so you can imagine that in a situation like this, if you have a lot of signals and a lot of traces, there's going to be current that's going to kind of overlap or run through each other, and that's going to create noise. It's going to create additional issues. Okay, and these are things that you have to become very aware of when dealing with the high-speed regime. So what's the key? Don't think of things in terms of a ground. You know, you really shouldn't ever just think of an infinite current sink. It's a good useful approximation when you're not in the high-speed regime. But if you just think about every trace that goes out of my IC, for example, out of my Arduino, has to come back to the battery, has to come back to the ground, has to come back. You know, you have a return, you have a signal path and you have a return path, and that happens for every single net. If you think in those terms, then you can become more aware of how your signal is behaving on the board, and that can help you troubleshoot issues. Okay, so those are the key concepts we kind of want to talk about here. Okay, and if we look at it, you know, since we're talking about ground, we're going to go ahead and talk about this side. Okay, the idea of ground and why just thinking in terms of a current sink is a problem. Okay, of just this one big plane and putting everything through there, everything's going to be okay. All right, if you look, these three circuits look identical, right? Because they're all going to ground. Okay, But depending on how they're routed, you may run into issues, okay? So let's take a look at the physical implementation, okay? So on one end, you have power coming into the component, obviously, and then you have it coming back to where it came from, okay? So in my case, this illustration I should probably update to have 2 points, for power coming in. So just assume for now that power's coming in through the rightmost capacitor on each of these, okay? So power comes in. If you were to daisy chain the connections, there is an impedance. Here we've modeled it as just a simple resistor, but it does have an impedance. It has a capacitance, has an inductance to it, okay? And as you can see here, if it's daisy chained, then this reference potential is going to be different from this reference potential. It's going to be different from this reference potential. Okay? And that can cause a circuit to not work. Okay? In these good examples, what you notice is that we're thinking about a return path. And that's what's reflected in the PCB. Okay? So in the schematic, I'm just making it really obvious. But if we go to the PCB, you're going to see that how the connections are made reflects this. Okay? And the reason a ground plane is good is that it can make it easy. It's giving lots of paths for the current to come back to its origin. Okay? And because it's just a plane of copper, most, unless the current is going through large distances, these impedances are going to be small. Okay? So that's what's really going on. You can still think of a copper plane as making it easy for all the return paths to go back to their origin. Okay, but don't think of it as just a sink of current, and as long as it's connected to the ground plane, everything is going to be okay, because that may not be the case. If we have a lot of signals going around here, you have to be careful on how you route them, because you may cause return paths to run over each other, to intersect, and that can increase noise. So keep that in mind. Okay, think signal path, return path. Don't think so much in terms of a ground. That's going to help avoid issues in the future. Okay, so let's kind of summarize what we've gone over. First, we've determined how we can see if we have high-speed signals or not. Okay, the simple rule of thumb, if you have clock frequencies higher than 100 megahertz and or rise times shorter than about 1 nanosecond, you have a high-speed signal, and you need to start thinking about signal integrity very, very carefully. Okay? Impedance is the language of signal integrity. Impedance is simply the relationship between a voltage and current in a conductor through a component. Okay? That relationship can be very complex, especially if you have an inductor or a capacitor. You're going to have phase shifting. You obviously have a frequency dependence. So impedance is more general than just resistance. Okay, so we're going to be talking the rest of this webinar series as we do them. We're going to be talking about impedance. Keep that in mind. Relationship between voltage and current. Very simple. Okay, for your signal integrity to be preserved, for your signal not to distort, it needs to see a constant impedance as it travels through your board. Okay, and those impedances should be matched to minimize distortion. Finally, the last concept that we've covered is ground. Okay, we've enhanced our understanding of what ground is. Okay, most of the time you can think of it as an infinite sink, but that's not technically accurate. Okay, every signal has a return path. If you think in terms of signal path and return path, then things are going to be easier, because you're going to pay as much attention to the return path as you do to the signal path. And if you have a ground plane, okay, the current that flows through the ground plane doesn't just uniformly distribute. In a future webinar, we're going to see that in order to minimize impedance, because the signal is going to flow through the minimum impedance. It wants to minimize it. And that occurs when it's right below the signal path or right next to it, as close as possible to it. That's when you get minimum impedance. Okay, and that's how currents want to flow in a ground plane. They don't just distribute evenly, like if you were throwing a drop of water into a bucket. Okay, it's actually picking a specific section of the ground plane to travel through. And if there's anything in the way, then that's going to change the impedance and it's going to add a little bit of noise. So if you have a via in the way of that clean return path, then the current's going to have to go around the via, and that's going to change your impedance. Okay? So those are the three fundamental concepts we want to take away from the webinar today. And those are going to form a building block for future webinars on signal integrity.